Hello and welcome to the MOOC on optical communications. In this module we will discuss fundamentals of semiconductor laser diode. For a proper understanding of this topic, namely the semiconductor laser diode, you need to actually have a extensive background in PN junction and its associated physics. So, semiconductor physics, unfortunately that is not in the scope of this course. So, we will be content with qualitative pictures of how a semiconductor laser operates, and then we will discuss the types of semiconductor laser diodes, and I will leave LEDs as something for a reading assignment. Okay. To begin with, let us consider an atom, such as a hydrogen atom which has a positive nucleus and one electron around its orbital, right. Now, this is the simple picture that we normally think of, an atom having a positive nucleus and then an electron that is revolving around. However, the electron cannot reside at arbitrary distances. Those distances are essentially quantized. If you look at the quantum mechanical picture, you do have a nucleus, that is fine, but there is no fixed orbit or anything. What you instead have is a quantum mechanical state in which there is a certain probability for finding the electron in that. Okay. And whenever a quantum mechanical object such as an electron resides in a particular quantum state or has a certain quantum state, then there is a certain energy associated with it. In the classical picture, this energy could be anything, it can be a continuous number. However, when you are considering the quantum mechanical properties, you will soon see that this energy is quantized. In fact, the word quantum or quantized simply means that you have to have a certain minimum or a certain unit of energy, and multiples of that unit is what is allowed for the electrons to be possessed. So, in a sense that if you consider a free atom, right, it is not subjected to any other force except for the force because of the nucleus and the electron attraction, then the energies that this particular electron can have will be some value, but that value will be quantized, and all this can be inferred if you were to solve the Schrodinger equation for this particular system. In fact, there is a nice relationship between energy and momentum for a free particle, which we will see shortly. If you look at the energy or the quantum state, the energy actually is degenerate in the sense that in one quantum state you can actually fit in two different, or rather one energy level you can fit in two different electrons. One electron with an arrow upwards is called as a spin up electron, and the other electron having the same energy, but its spin is downwards. Spin is a quantum mechanical property, it does not have any analogous quantity in the classical mechanics. Okay. So, spin is completely quantum mechanical. You can simply think of this as a label which the electron carries. If the electron label is up, then we pictorially represent it as having a upward vector. In case it is a down, we show that pictorially by drawing a vector or an arrow downwards. Okay. However, important point to note is that for an isolated atom, both spin up electron and spin down electron have the same energy. So, any time two different quantities have the same energy, we call that degenerate. You might have encountered this degenerate or degeneracy when you look at optical waveguides or microwave waveguides, right. It is sometimes possible to have two different modes having the same energy. Then we say that these modes are degenerate. If you go to the optical fiber example, then the X polarized mode and the Y polarized mode have the same energy. So, these are two degenerate modes, they have the same propagation constant, at least in an ideal fiber that we can think of. So, for an ideal case they are degenerate, for a non-ideal case they are not, but we are simply looking at the ideal case. So, an isolated atom free of any external forces will have a degenerate electric level, and you can fit at most 2 electrons in that energy level, because Pauli's exclusion principle states that you cannot fit in one more in this particular configuration. So, in the electronic configuration, finally spin up and spin down can be put in the same energy level. Okay. But that is the case of a single hydrogen atom entirely in the universe. Unfortunately, universe is not like that, and especially the semiconductor materials are not going to be looking like a free hydrogen atom, right. Rather, what happens is if you bring one atom close to another atom, right, the separation between these two atoms is called as the interatomic spacing, and it is denoted by various letters. So, let us choose R as a letter to denote interatomic spacing. Now, if you look at the total energy of the system as a function of this interatomic spacing, you see that for large interatomic spacing, the energy levels are essentially discrete. So, you have a spin up and a spin down, they occupy the same energy levels, and this R is very large, which simply means that you take these two atoms and then put them as far as possible, right. So, the energy of or this particular atom is not talking to this atom, and therefore, they are essentially free, and the energy levels there are degenerate. Okay. If they are of the same kind, then they have the same energy, and in each case you can fit in a spin up, spin down, spin up, spin down. Okay. However, as the interatomic distance starts to decrease, what happens is that after a certain critical R0, you will see that the energy levels actually split. So, you see that one energy level is called as the anti-bonding energy level, and the other energy level is called as the bonding level. Okay. So, you will actually see that it is kind of splitting, but the bonding level initially decreases and then starts to increase. So, there is a minimum energy configuration over here, wherein most of your electrons or most of the materials can actually lie. Okay. So, this is your minimum energy which appears for the bonding levels. Okay. So, this is the bond energy level, this is the anti-bonding energy level. This is for two atoms which are close to each other. Now, imagine a solid such as a semiconductor, silicon, germanium, in gas, aluminum, gallium, aluminum arsenide. So, these are all the semiconductor materials, and these semiconductor materials are actually solids. Even among solids, they are crystals, which means that there is the atoms are going to be placed very closely with respect to each other, and what is more, they are actually in a definite pattern, right. More or less they actually have a nice pattern to them. If the crystals were free of defects or impurities, then this pattern would go on forever in the 2-dimensional or the 3-dimensional, depending on what structure you are looking at. But this pattern, there is a basic lattice, and then this lattice keeps on repeating itself in all these directions, right. So, the key word here is that there are many atoms, right. You must have heard of the Avogadro's number 10 to the power 23. So, in a per centimeter or per mole, there is so many number of atoms. Okay. So, you can imagine as so many number of atoms are placed together, there is going to be interaction among them, which what it causes is that when the atomic spacing decreases as you pack in closely and closely, these energy levels, they will split into 10 to the power 23 values, right. Each energy level will split into 10 to the power 23 values. From the perspective of mathematics, this is still discrete, because you can still count 1, 2 all the way up to 10 to the power 23. However, for all practical purposes, the spacing between this 10 to the power 23 energy levels becomes so small, right. This is the total energy that is available. This you split into 10 to the power 23. The spacing is going to be so small that for all practical purposes, you can simply consider them to be a continuous quantity. Okay. So, you end up replacing this discrete energy picture by a band of energy. Okay. So, let me try and see if I can do a band. No, I can't do a band here. So, you can see that I am filling up the entire region over here, indicating that this is actually a band. Okay. So, it is bounded between this bonding and anti-bonding levels, but this has essentially become a band of energies. This happens only for the case where you are looking at solids, because your atoms are going to be placed so closely, and of course, they also have a certain pattern. This is the interatomic spacing or the atomic spacing between the atoms, and denoted by A. So, let us say if you are looking at A here, then you actually have one energy level down here, another energy level down here, but there is actually a band of energies in between, correct. So, you actually have a band of energies in between. So, this gives rise to the concept of energy level going and becoming energy band. And you must have heard definitely of two bands, one is called as the valence band and the other is called as the conduction band. And based on this band picture, we can differentiate three different solids. One is a conductor, the other is a insulator, okay, and a semiconductor or a semi-insulator is something that exists in between these two quantities, right. So, the characteristic of a conductor is that you actually have a conduction band and a valence band which are very close to each other. What do we mean by a conduction band and a valence band? Valence band is the largest occupied energy that you can have. Energy is going up in this particular way for the electrons. So, valence band is the largest band that is occupied by the electrons, okay. And then if you apply an external electric field in the form of a voltage, then these electrons will simply skip to the conduction band without any problem. In fact, in some very good conductors, the conduction band actually and the valence band both coincide, in the sense that they do not really require a lot of energy. A simple temperature increase is sufficient to bring about a large number of electrons from the valence band into the conduction band, okay. The gap between valence to conduction band is called as the energy gap. In short while we will discuss where these concepts are coming from. On the other hand, on the other extreme is an insulator. In an insulator, the energy gap is pretty large between the conduction and the valence bands, okay. So, the electrons here, they, if you have to promote them into the conduction band, require a rather large energy to be supplied. This can be done by supplying very intense light field, so that the photons are absorbed and then it can go to the conduction band, right. Or you have to apply a very high temperature, so that this insulator breaks down and becomes conducting. In fact, there is a certain electric field that you have to apply in order to break down this particular insulator, okay. So, once that happens, then of course everything becomes ionized and then you get a nice conductor in place of an insulator, but that happens under very extreme conditions. A wood, for example, under ordinary temperatures would be an insulator, right. Somewhere in between is where what you have as a semiconductor, okay. So, if you have the energy gap as Eg for a semiconductor, it is possible to, so normally the electrons are found in the valence band. So, if you do not apply a voltage, they are usually insulators. However, when you apply a voltage, they will jump from valence band to the conduction band, okay. As the electron jumps, it kind of leaves behind an empty space. The actual phenomenon is very deeply mathematical to tell you and deeply physical to tell you that, but this simple picture should be enough for us, okay. In this simple picture, whenever an electron leaves the valence band, it leaves behind a hole, okay. This promotion from valence band to conduction band can happen by an external electric field. It is not necessary that you have to always apply a photon in order to induce this transition, okay. So, this transition can happen by an external current being forced or something like that, okay. So, this is called as a hole, and whatever of course is actually here is an electron, okay. So, when an electron jumps from valence to the conduction band, it leaves behind a hole. The characteristic of hole is that it carries positive charge, which is exactly equal to the magnitude of the electron charge. So, it is exactly equal to the magnitude of the electron charge, okay. It is slightly heavy compared to the electron. It has a low mobility compared to the electron, okay. It has a low mobility, which means it kind of moves slowly compared to the electrons, and remember, this was the one which was actually limiting our response time in a photodetector, because in a photodetector whole response time was considerably longer than the electron response time, right. So, this is for all practical purposes behaves as a positively charged quantity. It is heavy, it has low mobility, and it, when you apply an electric field, it moves along the electric field, okay. So, that is another characteristic of this, while electrons always move opposite to the electric field. So, if you apply an electric field along the x direction, this will move in the opposite direction, okay. So, these are the semiconductors. This transition wherein an electron jumped from valence band to conduction band can be reversed under certain conditions, where an electron can jump back to meet with the hole, resulting in a generation of a photon of a certain frequency nu, which is dependent on the energy band gap, right. The photon energy that is released, if the atoms fall exactly when they recombine, the electrons recombine with the holes, will be exactly equal to the energy gap, okay, from which you can also calculate what would be the wavelength and everything, all these characteristic, and see whether these type of materials are suitable for optical communication. Remember, optical communication happens at around 1550 nanometer, right. The C band is around 1550 nanometer. Therefore, you require semiconductors whose energy gap is around Hc by lambda. Okay. So, if you find a semiconductor with this particular thing, then you will be seeing when they recombine, electrons and holes recombine, you will see a photon coming out. This process is called as electron hole recombination. Let us dig a little more deeper into this concept of band, right. We have already said that free electrons, that is free atoms which are subjected to no external field will have an energy E, which actually can be shown to be given by h bar k square, h bar square k square or h bar k square. There is actually a k square dependence. I think this is h bar square k square for the energy that is there here. If you actually plot this energy as a function of k, where k is the wave number, so quantum mechanically you picture the electron actually being described by a certain wave function. This wave function in the time domain can be described by giving its, in a one dimensional wave function can be described by giving x and t, assuming that the wave is along the x direction, or equivalently you can describe in the momentum picture or in the so called Fourier space by giving k and frequency f. Okay. So, this is the k that I am actually talking about, and in fact turns out that momentum p is related to the k vector or the k number by this relationship. P is the momentum and energy is basically p square divided by 2m, right. Therefore, this actually energy becomes h bar square k square divided by 2 into m. So, if you sketch this energy versus k, what you see is a nice parabolic way in which the energy increases. Okay. Maybe the figures are not very nicely drawn, but this is a k square dependence. Okay. This is a function of k square. This is your energy E. Is that okay? So, now with energy E depending as a parabolic function or changing as a parabola, right, it can have any value of energy you want. So, a given isolated electron can take on any energy level that it wants, and corresponding to every energy that it takes, there is a corresponding momentum k as well. That is what this particular graph means. For example, you want this electron E, energy E, the corresponding momentum. So, if this is say E0, then the corresponding momentum will be k0. Now, this picture unfortunately breaks down when you go to a solid. So, that was for the free space condition or when there is only one atom in the whole universe. Here on a solid, unfortunately you have so many atoms which are close by, and these atoms in turn talk to each other. Okay. In fact, there is a phenomenon which is very similar to the phenomenon that we talked about, a Bragg grating kind of a phenomenon, right. Remember the fiber Bragg gratings that we talked about. There is essentially a reflection of the waves which add in phase, creating energy gaps, right, and a same situation happens over here. So, what you get is this momentum gets quantized in terms of this pi by a units. So, this is k, the fundamental will be at minus pi by a to plus pi by a, giving you a total maximum change of 2 pi by a over this particular range. Okay. Then you have 2 pi by a, you have 4 pi by a, or rather 3 pi by a and so on. Here you have minus 2 pi by a, minus 3 pi by a and so on. So, these are the different momentum ranges. Okay. Sorry, it is not momentum which gets quantized, it is the energy which gets quantized. Actually what happens to the energy then is, here it is still parabolic, okay, which is fine. So, it is still parabolic. At the edge, this is called as a band edge, or the at the edge of the value here at pi by a, because of the Bragg type of reflection, this energy kind of goes or bends slightly. Okay. Then what happens, the next energy levels, there is actually a gap over here, and then the next energy level goes from pi by a to 2 pi by a. Okay. Similarly, here it will go from pi by a to 2 pi by a. So, let me try and make this symmetric because they are actually symmetric. So, here you actually get symmetric condition here. At this point you actually get a small bending, and this is how you are going to get. Okay. This is because I have kind of drawing the graphs not very nicely, but this is what happens. So, there is a small amount of bending here, and this is the type of bending that you are going to get. Look at this, in this region, right, in this region you see that there is a gap, correct. If you try and find out what would be the corresponding, if you want that this particular energy to be there, then you see that for this momentum, you know, the corresponding energy cannot exist. In other words, electrons are forbidden to actually have this energy. Okay. This is called as the energy gap. There is a next level at which this one will change from pi by a to 3 pi by a, and then it will again change here, there will be a slight bending again, but what you see here is a gap, right. Again there will be an energy gap, this gap may reduce in magnitude compared to the earlier gap and so on. So, the energy gaps also start reducing as you go ahead as it is, right. Now, this is the energy momentum diagram, okay, or sometimes called as the energy band diagram, but then this energy band diagram shows that k can take on an infinite number of values, but there is a certain periodicity to the crystal. The crystal is actually periodic with a period a. Therefore, the fundamental period of the crystal in terms of the frequency units is 2 pi by a, right. If capital T is the period of the waveform, then the fundamental frequency will be 2 pi by t, and the fundamental range is minus pi by t to plus pi by t. So, going with the same concept there, the fundamental period will be 2 pi by a, which you can spread it out into minus pi by a to plus pi by a. So, all the other energy band diagrams outside this interval can be pulled back by translating them by a factor of integral multiple of 2 pi by a. So, if you translate this one, okay, if you translate this by a factor of 2 pi by a, then what happens is this one goes to, this is already pi by a. So, you translate this one by minus 2 pi by a. So, this fellow goes to here, and this edge, the top edge goes to 0. Okay. So, this band goes and becomes something like this. This band here will be translated by a factor of pi by a, I mean when you add a 2 pi by a to bring it to the primary region, this fellow will go here and this bend edge will go to 0. So, you actually get a band that looks like this. So, writing it separately out, this is how the energy and k diagrams would look like. So, this is your k, this is the fundamental which is almost parabolic, but just slightly bending at the edge, and then you have the next level which shows like this, right, and then the next level is again parabolic. You can show why that is parabolic by going to the upper picture and then translating these fellows back into 2 pi by a range or into the fundamental range. Okay. This again has to be symmetric with a 0 sitting at the origin. So, let me just draw it here. So, the 0 is sitting here. Okay. So, this is your parabolic thing. Okay. Suppose in a particular semiconductor, this happens to be the valence band edge. Okay. Then this happens to be the conduction band edge, and the difference between these two is the energy gap that we are looking for. If you look at this energy band gap diagram, you see that the top of the valence band is directly below the bottom of the conduction band. Okay. Semiconductor materials which actually have this particular characteristic are called as direct band gap materials, and example of a direct band gap material is gallium arsenide, okay, or indium phosphate in gas P, right. So, in gas P is also a material that has direct band gap. In contrast, there are certain materials for which the valence band edge and the conduction band edge are not at all coinciding with each other. So, the top here is way off from the bottom of the conduction band over here. Okay. Then this is a very important situation because this corresponds to silicon, for example, and as you know, silicon is the base material that is used for all VLSI ULSI circuits, and the silicon technology is very well developed. Unfortunately, that cannot be directly be used for optical integrated circuit realization, because silicon is not a direct band gap material. This is called as a indirect band gap material because the conduction band sits here and the valence band sits here. Why is this very important? It is important because it is possible for the electrons. So, here is all the electrons which are sitting up there, and here is all the holes which are sitting. Okay. It is possible for these electrons to make a transition from energy, from the conduction band to the valence band, thereby generating a photon. If you did not have exactly the top level transition, maybe the electron sitting here might want to transit down here. If I blow this up and then show it to you, it looks like this. So, the electron that is sitting here is making a transition onto the hole here, in the process generating a photon h nu. Okay, please remember, this is a highly exaggerated picture. This is not the same scale as this one. Okay, I am just showing it because I can't draw an arrow and make it show it to you in a nice clear way. So, when this happens, the photon actually, the energy corresponds to a certain momentum h bar k. This has a so let us call this as h bar k e, and this call it as h bar k h. Okay, k h stands for the hole, k e stands for the electron. So, when the initial state of the momentum is h bar k e and the final state of the momentum is h bar k h, there is a difference between these two momentum, right, and this difference momentum, which is h bar delta k, has to go into the photon. And what is the maximum such difference that can happen? The maximum such momentum change can happen when delta k changes by 2 pi by a, right. So, that is the maximum transfer or the longitudinal or the change in the momentum that can be possible. Come back to this indirect band gap material. The electrons which are sitting up here cannot directly fall down here, right. That is because these are all the valence band edges, they are all completely occupied. These are all occupied over here. There is no way you can transit and then find a final state. On the other hand, if it has to make a transition, then it has to make a transition this way. You look at the amount of delta k that is required. This delta k is almost going to its maximum value of 2 pi by a, whereas here the corresponding delta k is actually very small. This is about 10 to the power minus 4, because you can show that the relative delta k that is necessary will be somehow will be given by a by lambda, where a is the interatomic spacing, which maybe for many cases is 1 angstrom, that is 1 into 10 to the power minus 10 meter. And if you are looking for emission of 1 micrometer light, so this is the delta k change that you want, right, the normalized delta k that change that you want, which is around 10 to the power minus 4. On the other hand, for a indirect band gap material, this change is very large, because delta k that you have to get should be 2 pi a times something, and that would be pretty large, because it is the one band edge to the other band edge transition. So, result being most of these transitions end up as heat rather than actually giving rise to a radiative transition. So, we will stop here, and in the next module we will talk about the semiconductor laser diode, okay, formed by a p-n junction. Thank you very much.